In this lesson, I'm going to teach you a special trick that you can use to solve algebraic problems in one step. Now on a high level, when you're actually performing algebra, you're trying to find the value of some missing variable. So let me tell you the trick right up front. You want to do the opposite steps in the opposite order to find the missing variable that you're after. To properly understand what I mean by this, I'm going to give you an analogy. I want you to imagine that you started off with some kind of gift that you wanted to give to a friend. So you got your friend a new pet teddy bear, but before you give it away, you decide to put it in a box for them. Now once you've got the bear firmly in the box, the next thing you decide to do is to actually wrap it with wrapping paper. But of course, you can't give a present without a ribbon, so you decide to actually put a ribbon on the box too. Now once you actually hand this present to your friend, I want you to notice that they're going to do the opposite steps in the opposite order to actually find out what the present is. They're going to start by actually untying the ribbon, and then they're going to unwrap the box. After this, whatever it is you had inside, they're going to take it out of the box. Now, to extend the analogy further, this is the order of operations that you applied. And then when your friend undid the operations, this is sort of like what you would be doing when you actually perform algebra. So the whole idea is that you started off with some unknown variable. Then you applied some operations to it. After you've actually done those operations, you end up with something that doesn't really resemble the initial thing you started with at all. But if you do the opposite steps in the opposite order, you can actually recover the thing that you started with. And that's the whole spirit of algebra. So using numbers, we can say that if the order of operations takes some number x and say add 6 to it, then you're left with x plus 6. So this is the order of operations. But then algebra is going to be the undo button. It's going to undo the order of operations. And I hope you understand that every single operation has an opposite operation. So for example, the opposite of adding 6 is subtracting 6. And the opposite of, say, multiplying by 3 is dividing by 3, and so on. But these are all just words until you actually see an example. So let me bring one up. Okay, so here's a nice problem that we can solve with algebra. Suppose Langdon makes $3 of profit every time he makes a toy. He pays $4 per day to maintain his tools, and he gives 1/8 of all of his profits to charity. If he gave $7 to charity today, how many toys did he make? Okay, so to solve this problem, suppose that the number of toys he made today is the letter T. Now, if he made 10 toys, for example, he would have made $30 of profit because he makes $3 of profit every time he makes one toy. So to get the amount of profit he's made, you just multiply T by 3. After we figure out how much profit he's made, we have to remember that he pays $4 to maintain his tools. So we have to subtract 4 from the total amount he has so far. Now, after actually fixing his tools, we know that he gives 1/8 of the remaining money to charity. So to figure out exactly how much money he gave to charity, we just have to divide this number by 8. But in this problem, we're told that the amount he gave to charity equals 7. So we can also write that over here as well. Now, if you look carefully, I hope you notice that this is very much like taking this teddy bear, putting it in a box and then wrapping it. You've just applied a bunch of operations, and now you just want to undo them. Well, to undo them, we know that we just apply the opposite steps in the opposite order. So if we have the number 7 over here, we know that in order to undo division, we have to actually multiply by 8 to get from here to here. And we know that 7 times 8 is the same thing as 56. So that means over here, he had $56 left after he fixed his tools. And this actually makes sense if you just look at it again. We know that if you had 56 and you divided by 8, you'd just be back at 7 again. So this is actually the correct number over here. But then if you want to go back even further, you have to understand that to go from the profit to the amount he has after fixing tools, we just subtracted 4. So that means to go backwards, we just have to add 4 to go from there to here. So we know that 56 plus 4 is the same thing as 60, so we can write that down too. And we know this is true as well, because 60 minus 4 is the same thing as 56. So we know that before actually giving any money away, he had exactly $60 in profit that day. Well, the last thing to do is to undo this multiplication by 3. We know that the opposite of multiplying by 3 is dividing by 3. So we have to divide by 3 to go from here to here. Well, as we know, 60 divided by 3 is the same thing as 20. So that means, today, Langdon made exactly 20 toys. Now I think it's actually pretty cool that we solved a problem like this just by drawing a picture. But we should also see how things work symbolically as well. So if we started off by writing the letter T, the first thing we did is we multiplied it by 3, so that would just give us 3t. After this we subtracted 4, so we should just subtract 4 from 3t. And then, after getting here, we just divide by 8, so we'd get 3t minus 4 all divided by 8. Now this 3t minus 4 all divided by 8 is going to be the amount of money he gave to charity. But the problem tells you that he gave $7 to charity, so we know this all equals the number 7. Now to solve this problem symbolically, the first thing we do is multiply everything by this number 8. So what I'm going to do is, I'm going to multiply both sides by 8, because as we know, multiplying both sides by something doesn't change the value. So you can see that on the right, we just have 7 times 8, which is the 56 we had before. And then on the left, we can see that these 8's cross out, which gives us 3t minus 4. So this term must also be the same thing as 3t minus 4. But instead of being really mechanical and thinking of multiplying both sides by 8, one thing I want you to understand is that these two just end up going away. So it looks almost like you've taken this 8 and just multiplied it across to the 7. And these sort of animations make it really easy for you to actually do algebra in your head. So instead of actually thinking of multiplying both sides by 8, what I always imagine is I imagine taking this 8 and just throwing it over here. Now the next thing we're going to do is we're going to add 4 to both sides. So imagine adding 4 here and then adding 4 here. Of course on the left these two would just cross out and this would just stay on the right hand side. But of course I like to think of this differently. I want you to imagine actually taking this minus 4, moving it to the other side and then swapping any minuses for pluses or vice versa. And now the last operation we applied is this division by 3. So that means we're going to divide both sides by 3. And that's perfectly okay because these 3's will cross out, leaving you with a t. But again, instead of doing that, I'd like to do it another way. I want you to imagine actually taking this 3 and throwing it underneath the whole term on the right. Because that's kind of the opposite of the multiplication, which we did over here. So from this you can see that this gives us the exact same result. Notice that we started with 7 and then multiplied by 8, as we have here. Then we added 4, and then we just divided by 3, which we have over here. Again, no matter how you do it, you're always going to end up with a final answer of exactly 20 units. So Langdon made 20 units. But there are quite a few things that can go wrong. So let me actually go ahead and show you the first of them. Now there are actually some operations that require extra care while you're trying to undo them. For example, if you started with some number x and then you squared it, you'd actually end up with a number 9, for example. But you need to notice that there are actually two numbers that you can square to get the number 9. You could square 3 to get 9, but you could also square negative 3 to get 9. So the thing to remember here is that anytime you square a number, the opposite is the square root. But anytime you try to square root a number, you have to remember that your answer could be positive or negative. So in other words, we can say that if x squared equals a, then when you try to actually undo the square, you have to say that x is equal to plus minus the square root of a. Now again, rather than just telling you that, let me show you an actual example and we'll work through it together. Okay, so here's another problem here. We're told that Fiona has a square block of chocolate. She breaks off exactly 3 rows and 3 columns, then she takes 6 of the blocks she broke off and puts them back. If she is left with exactly 7 blocks, how wide was the original block of chocolate in squares? Now suppose Fiona started off with a block of chocolate that was x blocks wide and x blocks tall. Well, we were told that she snapped off exactly 3 blocks from the rows and from the columns. Now if she started with x blocks and then she took away 3, then she's got whatever she had minus 3, or x minus 3 blocks by x minus 3 blocks. After this, we were told that she put back exactly 6 blocks, so we can draw them in as well. So after she's taken away her blocks, there are exactly x minus 3 times x minus 3 blocks left over, and then there's the 6 that she added back on. So she has x minus 3 squared plus 6 total blocks. Now after all of this is said and done, we told you that she has exactly 7 blocks left over. So that means this x minus 3 squared plus 6 equals the 7 blocks that she's left over with. Another way to also visualize this problem is to imagine starting with x blocks. So if you started with x, the first thing she did was she took away 3, so you have x minus 3. Now after this, once you've got x minus 3, you have to square it to turn it into this square, so we have x minus 3 squared. After taking this square, we then added on that 6, so we can add 6 to this as well. But then after all of this, we were left with exactly 7 blocks. Well, to figure out what x is, again we just have to do the opposite steps in the opposite order. So the first thing we do is, instead of adding 6, we have to subtract 6 to go from here to here. But then 7 minus 6 is the same thing as 1. And if you think about it, that makes sense. If she has 7 blocks in total, if there are 6 over here, then this one must represent 1, despite the way I've drawn it. So now the next thing we want to do is we want to undo this square over here. But as we already discussed, the opposite of a square is a square root. And anytime you want a square root, you have to remember to add plus minus in front. Now of course, the square root of 1 is just the number 1. But you have to remember to include plus minus 1, because minus 1 squared is also 1, as is 1 squared. So now that you've got this plus minus here, to go back one more step, we have to understand that the opposite of subtracting 3 is adding 3. So in the case that this number over here was minus 1, then we'd actually add 3 to get the number 2. But in the case that the number was actually positive 1, if you add 3 to it, you'd get the number 4. So this just tells us that Fiona could have either started with a 4x4 block of chocolate or a 2x2 block of chocolate. Now once you have an answer like this, you have to inspect it and see whether or not it actually makes sense. If you actually inspect these answers, you notice that Fiona could not have started with a 2x2 block of chocolate, because after all, she snapped off 3 rows and 3 columns. So if she started with only 2 chocolates here, then when she snapped 3, she would have ended up with minus 1 chocolates. So that means she must have had a 4x4 block. Now again, it is also completely possible to repeat these steps symbolically. So the first thing I want you to imagine is I want you to imagine throwing this plus 6 over to the other side. And remember, plus signs turn into minus signs when you do that. After this, you have to imagine actually throwing this square sign to the other side as well. We know that squares turn into square roots, but you have to remember to add on this plus minus over here. So now, to get the x on its own, you just have to actually take this minus 3 and move it to the right as well, remembering to swap the negative for a positive. Now of course, if you evaluate this, you'll see that 3 plus minus root 7 minus 6 is the same thing as 3 plus minus 1, and that's the same thing as either 2 or 4, so you just get the same answers we got up here. Now it is totally possible for you to solve the problem symbolically or by drawing out these diagrams. I think while you're starting, you should try both. Try doing both methods and actually seeing how they map to each other. The great thing about this method over here is it tells you exactly what steps to take and exactly what order you should take them in. But if I'm being totally honest with you, this does not always work. There is actually one particular case that you need to look out for because it can actually cause you quite a bit of trouble. So let's examine that now as well. Okay, so this problem over here doesn't actually look much harder. We're asking you to solve for x when x divided by 4 plus 3x minus 7 is equal to the number 2. Well, let's try doing this by just starting with the order of operations again. The first thing I want to do is I want to start by actually drawing out this number x. Okay, so if you start with the letter x, the first thing we're doing to it is we're dividing it by the number 4. So let's draw that. But then in this term over here, we're taking the number x and then we're multiplying it by 3. So we can draw that in as well. Okay, so over here, we just have the number x divided by 4. And then over here, we'd have the number x times 3. We can see over in this expression that we want to add x divided by 4 plus x times 3. So we should just add an addition node here and actually add them. Okay, so once we've added x on 4 and 3x together, then we have this number here. And then from this number, we have to subtract 7. So we can do that too. So once we've done all of this, we know that x on 4 plus 3x, or minus 7, is equal to the number 2. Okay, so now that we have this, let's try actually finding the value of x in this problem. Well, we know that we have 2 over here, and the opposite of subtracting 7 is adding 7. So therefore we can write that 2 plus 7 is the same thing as the number 9. So we definitely have the number 9 over here. But now we actually hit a really big problem. How much of the 9 goes here, and how much of the 9 goes here? Well, there's really no way to know, and that's actually the biggest problem with problems like this. So then you might wonder, what's so different about this problem that caused it to go wrong? And the answer is actually pretty simple. The simple fact that we have more than one x here means that we need to take more than one possible branch to get to the final answer. So this immediately tells us that it's impossible to actually solve for x if we have more than one x in our particular problem. So therefore, whenever we want to actually try solving a problem like this, we have to find a way to convert it into an equivalent problem that contains only one x. So in this lesson, I don't want to actually solve this problem, but I just want you to be aware of the fact that it exists. When you have only one x, it is actually really easy to solve the problem. So a lot of the trouble is going to be finding an expression that contains only one x, given one that contains more than one. So let's just write down this important lesson and summarize everything we've learnt. So from that last example I gave you, it's important to understand that this technique is only going to work when there's exactly one pro-numeral in the expression you're trying to solve. In this lesson, we likened algebra to starting off with some number or some item, and then doing some operations to it. Once you've done those operations, algebra aims to do the opposite operations in the opposite order. If you do this successfully, you can take some complicated expression and then recover the original thing that you started with. After this, we saw that some operations, like the square, are not so easy to undo. For example, if you take x and square it, you have to remember that when you square root, you must include a plus minus in front. However, the square root does not actually suffer from this problem. For example, the square root of the number 9 is actually the number 3, and then if you square 3, you'll just get back to 9. It's only when you actually try to undo the square that problems occur. Now in the future, you're going to see a lot more operations that don't have a very simple undo button, and when you actually try undoing them, you have to look very carefully at what might go wrong. Then after this, we saw that this technique only works if you have exactly one pro-numeral in the expression. Now that might seem like a really big dampener, but it's actually not so much of a big problem. In the lesson where I explained what an expression actually was, I said that it's possible to write lots of expressions that are equivalent to each other. So in order to get around this problem over here, we just need to find an expression that's equivalent to one that we cannot solve, and it should contain one pro-numeral. So therefore, the rest of our studies of algebra are going to be to find ways to convert expressions that contain more than one pro-numeral into expressions that contain only one pro-numeral. And to actually see this in action, you'll want to tune in to the next lesson. So I'll see you there. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.